Okay, we're continuing with Chapter 2 in the chemistry textbook. In this video, we're going to go through the last two sections, which talk about naming compounds, the nomenclature for compounds. So remember, a compound, if we think about how all matter is categorized, a compound isn't a mixture. It's the pure form of a substance, to where you can think about, you can represent a compound with it's just a single chemical formula. So like H2O, this is a compound, or like a silver nitrate. This is a compound. Whereas if you had a mixture, you would have to sort of put, okay, here's one component of the mixture, and then put another chemical formula. But now compounds aren't elements. You know, you could have H2. Well, we're not talking about naming H2. That would be hydrogen, right? Just a certain allotrope of hydrogen. So we're talking about in this section, a compound is the pure form of a substance with two or more elements. And so what's the naming convention for, how do we name this? This is silver nitrate. Why do we call this silver nitrate? Why do we call this water and not dihydrogen monoxide? Okay. When chemistry was a young science and the number of known compounds was small, it was possible to memorize their names. Many of the names were derived from their physical appearance, properties, origin, or application. For example, milk of magnesia, laughing gas, limestone, caustic soda, lye, washing soda, and baking soda. Today, the number of known compounds is well over 66 million. Fortunately, it is not necessary to memorize their names. Over the years, chemists have devised a clear system for naming chemical substances. The rules are accepted worldwide, facilitating communication among chemists and providing a useful way of labeling an overwhelming variety of substances. Mastering these rules now will prove beneficial almost immediately as we proceed with our study of chemistry. To begin our discussion of chemical nomenclature, the naming of chemical compounds, we must first distinguish between inorganic and organic compounds. Organic compounds contain carbon, usually in combination with elements such as hydrogen, oxygen, nitrogen, and sulfur. All other compounds are classified as inorganic compounds. Okay, so that's interesting. If we think about any compound in the universe, which again is, you could just think about as just a simple chemical formula. It could be a complex chemical formula, but it's one single chemical formula that has at least two elements in it. All chemical compounds we can put into two categories, as the categories being organic or inorganic. Okay, now it says organic compounds you think about as containing carbon, usually in combination with elements such as hydrogen, oxygen, nitrogen, and sulfur, but then all other compounds are classified as inorganic. Now, this is not a foolproof way of labeling organic compounds because we know, so it says for convenience, some carbon-containing compounds such as carbon monoxide, carbon dioxide, carbon disulfide, and compounds containing the cyanide group and carbonate and bicarbonate are considered to be inorganic compounds. So there are some compounds that contain carbon that we don't call organic, right? Like carbon dioxide. That's not, we don't look at that as an organic compound. And so then, well, you can't just say that an organic compound is any compound that contains carbon. So what is an organic compound then? Well, in general, an organic compound is going to be associated with living organisms. You might say, well, what about like hydrocarbons, gasoline? Well, yeah, that's all been broken down by living organisms, right? Oil comes from, its origin is living organisms. Okay, but now there's forms of organic compounds that are synthesized in labs, and so they're not produced by living organisms, but they're still associated with living organisms. You have like biological molecules like carbohydrates, proteins, lipids synthesized in labs. So it's really organic compounds in general. They're going to contain carbon and be associated with living organisms, as opposed to like cyanide and carbon dioxide are not. Okay. To organize and simplify our venture into naming compounds, we can divide inorganic compounds into four categories: ionic compounds, molecular compounds, acids and bases, and hydrates. So, okay, we're going to start with inorganic compounds. Once again, inorganic compounds we can put into 4 categories: ionic compounds, molecular compounds, acids and bases, and hydrates. So we're going to start with ionic compounds. We know that an ionic compound is made up of, it's a bond between a cation and an anion, right? Okay. So how do we name ionic compounds? And really, we're also going to need to know how do we name cations and anions as well. In section 2.5, we learn that ionic compounds are made up of cations, positive ions, and anions, negative ions. With the important exception of the ammonium ion, NH4+, all cations of interest to us are derived from metal atoms. Okay, so the name of any ionic compound between, you have a cation and an anion, is going to be, you state the name of the cation and then immediately state the name of the anion. So to do this, we need to understand the names of cations and anions. All right, now, so it's saying with the exception of the ammonium ion, NH4+, so nitrogen and hydrogen aren't metals, but hydrogen is special. Even though hydrogen is technically classified as a non-metal, it can chemically behave in different circumstances like both a metal and a non-metal. It can act electropositive in some cases, more rejecting electrons, and electronegative in other cases, more of accepting electrons. But with the exception of ammonium, the cations that we're going to focus on, which is most cations anyway, are going to be derived from metals, metal atoms. Okay, and metal cations take their names from the elements. For example, sodium, the sodium cation is just called sodium cation. So for the monoatomic case of a metal cation, so we're dealing with a single atom, a single element, single atom of a metal cation, the name is just the element name itself, followed by ion, right? The sodium ion, the potassium cation, the magnesium cation, the aluminum cation. And it doesn't matter what the charge is, right? Magnesium 2+, aluminum 3+. It's still just the aluminum cation. Okay, many ionic compounds are binary compounds, or compounds formed from just 2 elements. So, okay, binary compounds. And we're going to learn in a second the term ternary compounds. So this is different from earlier in the chapter we learned about monoatomic, biatomic, diatomic, polyatomic. Those terms were based on how many actual atoms are in the molecular compound. So H2 would be diatomic. H2O would be not biatomic, but polyatomic. There's 3 total atoms. But as a compound, H2O would be a binary compound. There's just 2 total element types. H2 isn't a compound, right? So we're going to think about binary compounds and ternary compounds. A ternary compound would be something like, right, there's 3 different types of atoms here, or types of elements here. So this would be polyatomic, 3, 4, 5 atoms, but since there's only 3 types of elements here, it's a ternary compound. Okay, so many ionic compounds are binary compounds, or compounds formed from just 2 elements, like NaCl, right? 2 elements. For binary compounds, the first element named is the metal cation, followed by the non-metallic anion. Thus, NaCl is sodium chloride. The anion is named by taking the first part of the element name, chlorine, and then adding "-ide." So yeah, with a binary ionic compound, 2 elements, it's made up of just 2 types of elements. The name is, you say the cation name, and then you say the anion name. We just talked about the names for cations, specifically monoatomic metal cations, which is going to be the majority of cations anyway, are going to be at least metal for sure. Okay, now what about the name of a monoatomic anion? What you do is you take the element name and then replace the ending with "-ide." So if we come here, you have, so carbide, sulfide, nitride, phosphide, oxide, sulfide, selenide, telluride, fluoride, chloride, bromide, iodide. Note that these are monoatomic. So the ion associated with O2 is going to have a different name than oxide. So the cations and the anion names we just talked about are based on, or they're monoatomic ions. Okay, so we've got KBr, that would be potassium bromide, right? Potassium that's the name of the potassium cation. Potassium, the name of the bromine anion is bromide. Zinc iodide, aluminum oxide. Okay, the "ide" ending is also used for certain anion groups containing different elements, such as hydroxide and cyanide. Thus, the compounds LiOH and KCN are named lithium hydroxide and potassium cyanide, respectively. So, okay, what they're saying is, for the case of an anion that has more than one type of element, to where you can't just take the element name and put "ide" at the end, in some cases, these anions are named with an "ide" anyway, just to indicate that you're dealing with an anion. But we're going to see that's not always the case, though. These and a number of other such ionic substances are called ternary compounds, meaning compounds consisting of three elements. Yeah, KCN and lithium hydroxide. There's three total elements. Table 2.3 lists alphabetically the names of a number of common cations and anions. Okay, certain metals, especially the transition metals, can form more than one type of cation. Take iron as an example. Iron can form two cations, Fe2+ and Fe3+. So, okay, there's certain metals. We're talking about cations right now, so we're focused just on metals, which again is going to be the vast majority of cations anyway. Okay, there's certain metals, especially the transition metals, that can form more than one type of cation, meaning in relation to the charge of the ion, like Fe2+ and Fe3+. An older nomenclature system that is still in limited use assigns the ending "us" to the cation with fewer positive charges and the ending "ic" to the cation with more positive charges. So the ferrous ion and then the ferric ion. The names of the compounds that these iron ions form with chlorine would thus be ferrous chloride and ferric chloride. Okay, but this method of naming ions has some distinct limitations. First, the "us" and "ic" suffixes do not provide information regarding the actual charges of the two cations involved. Thus, the ferric ion is Fe3+, but the cation of copper, named cupric, has the formula Cu2+. Yeah, so it's not like every single transition metal that can form that forms two different ions is going to be a +3 and a +2, like iron. So like copper, it's a +2 and a +1. So, okay, in addition, the "us" and "ic" designations provide names for only two different elemental cations. But some metallic elements can assume three or more different positive charges in compounds. Yeah, so with just "us" and "ic", what about, like they show here, manganese? Therefore, it has become increasingly common to designate different cations with Roman numerals. This is called the stock system. In this system, the Roman numeral 1 indicates one positive charge, 2 means two positive charges, and so on. For example, manganese atoms can assume several different positive charges. So Mn2+, Mn3+, Mn4+. So the name of the cation in this case, right now we're talking about cations that can form more than one type of ion with more than one type of charge, and specifically the transition metals. The name of the cations of a transition metal, assuming it can form more than one type of ion, you just state the element name and then put a Roman numeral indicating the charge. That's it. That's the name of these types of cations. And you state it or write it out, the name, as like this would be manganese 2, manganese 3, manganese 4. So that's the name of the cation. And then when you state the anion, just state the anion like we've discussed so far. In this case, we're dealing with an oxygen anion, oxide. And so with the stock system, we denote the ferrous ion and the ferric ion as iron 2 and iron 3 respectively. Ferrous chloride becomes iron 2 chloride, and ferric chloride is called iron 3 chloride. In keeping with modern practice, we will favor the stock system of naming compounds in this textbook. Okay, and so now here's some names and chemical formulas of common inorganic, we're focusing on inorganic at the moment, cations and anions. So what did we just learn in this section? We can go through these. If we're dealing with the name of any ionic compound that's just a bond between a cation and an anion, is you state the name of the cation, then you state immediately following, you state the name of the anion. That's it. The names of cations that we talked about were for a monoatomic cation that only can form one possible ion. You just state the element name. That's it. Aluminum. It doesn't matter what the charge is. Aluminum, the aluminum cation. Cesium, calcium cation. Cadmium cation. Silver cation. Strontium cation. Charge doesn't matter. Okay, if you have a monoatomic cation that can form more than one possible cation, and we focused on the transition metals here, then you state the name of the element, and then you use a Roman numeral to indicate the charge. So the chromium 3 cation, cobalt 2 cation, iron 3 cation. Okay, now cations that contain more than one type of atom, we didn't get into any details, but we mentioned the special case of the ammonium cation, NH3+, which actually doesn't even contain a metal element. All right, anions, if you're dealing with a monoatomic anion, so not just one type of element, but just also monoatomic as well. Same with cations. So we didn't make any statements about if you had something like Ag2 or something. You know, it's still a single type of element, but it has more than one atom, like you have oxygen as oxide, and then O2, 2 minus is going to have a different name. So monoatomic, single element monoatomic anions, the name is going to be, you just take the element name and replace the end with an "ide." Okay, and that's all we really talked about in relation to naming anions. We did also briefly mention how anions composed of more than one type of element, in some cases are going to be named with the "ide" in the end, just to indicate you're dealing with an anion. So peroxide, cyanide, hydroxide, for example, but this isn't always the case. I mean, we have nitrate here, chlorate, carbonate, etc. Okay, now, molecular compounds. Naming molecular compounds. So we're still talking about inorganic compounds. We just talked about how to name ionic compounds, bonds between a cation and an anion, or cations and anions. So now with a molecular compound, a molecular compound is not made up of ions. It's just these clusters of you can think about it just atoms bonded together. So a water molecule is going to be, you think about it as just two hydrogen atoms bonded to an oxygen atom. That's the discrete unit of a water substance, a water compound. It's made up of these H2O molecules. And so that's we represent this compound with the chemical formula H2O, right? So if the chemical formula is not corresponding to an ionic compound, but to a molecular compound, what's the naming convention? Okay. Unlike ionic compounds, molecular compounds contain discrete molecular units. They are usually composed of non-metallic elements, right? H2O. Those are non-metals. HNO3, hydrogen chloride, hydrogen bromide, silicon carbide. Those are all non-metals. Many molecular compounds are binary compounds. So composed of just two, that's not diatomic, that's binary, right? These are all actually diatomic and binary, but H2O is polyatomic but it would be a binary compound. Naming binary molecular compounds is similar to naming binary ionic compounds. We place the name of the first element in the formula first, and the second element is named by adding "ide" to the root of the element name. Okay, so this is a little bit different than it's obviously very similar to naming ionic compounds, but the difference you want to note is with an ionic compound, the chloride is specifying the chloride anion, right? The bromide anion. With ionic compounds, these two words are expressing or identifying the ions. Here, you still have in general, the original atoms, the original hydrogen atom, the original chlorine atom, but it's still named the same way for a binary ionic compound, and in this case, it's just or diatomic, right? We could have a binary molecular compound, but it's not diatomic. We'll talk about that in a second. But if it's just two total atoms and two different types of elements in the molecule, then you name it the exact same way as you do an ionic compound. Okay, now, but it says it is quite common for one pair of elements to form several different compounds. In these cases, confusion in naming the compounds is avoided by the use of Greek prefixes to denote the number of atoms of each element present. So this doesn't happen with ionic compounds. Well, okay, it kind of does in the case of if involving a transition metal, but we have distinct names for the ions associated with the different charges of transition metals. What I mean by that, this doesn't happen with ionic compounds is, so like you have carbon monoxide and then you also have carbon dioxide. There's no, if you had aluminum oxide as an ionic compound, well, there's no other ionic compound with different proportions, right? Because you only have O2 minus and Al3 plus. And then again, in the case of, okay, well, you could have like iron 2 plus or iron 3 plus, but we assign distinct names to those iron ions. So, okay, but with a molecular compound, you can have different compounds for the same pair of elements. So we're still talking about a binary compounds here, but now they're not necessarily going to be diatomic. So what do? We just use these Greek prefixes in front of the names as needed. So here, the convention is, so, okay, you use mono if need be for the second element in the compound. Again, this is still binary compound. You use mono if needed for the second element, but you omit the mono if needed for the first element. So you're not going to say monocarbon monoxide here. You would just say carbon monoxide. Okay, carbon dioxide, sulfur dioxide, sulfur trioxide, right? You just use the prefix as needed. But now here, we since it's not an N1, we are going to use the prefix for the first element, dinitrogen tetroxide. Okay, now, but also what's commonly done is for oxides, the ending A in the prefix is sometimes omitted. So the tetra, penta, hexa, the A here, just because it sounds smoother, it's typically omitted. So you would say dinitrogen, not tetraoxide, just tetroxide. So any of these prefixes with an A, ending in an A, if you're going to put that in front of an oxygen, you just omit the A because it sounds smoother. Exceptions to the use of Greek prefixes are molecular compounds containing hydrogen. Traditionally, many of these compounds are called either by their common non-systematic names or by names that do not specifically indicate the number of hydrogen atoms present. Right? So if we look here, none of these compounds contained hydrogen. Right? So what they're saying is, once again, we're still focused at the moment on binary molecular compounds. If one of these molecular compounds contains hydrogen, then that's an exception to the use of the Greek prefixes. Traditionally, many of these compounds are called either by their common non-systematic names, like water, right, or by names that do not specifically indicate the number of hydrogen atoms present. So diborane, methane, silane, ammonia, phosphate, water, hydrogen sulfide. So here, these are all the non-systematic names, right, like water. But then here is an example of the last thing this sentence mentioned was that it still uses the ionic compound type naming convention where you do the element name first, and then the second element is the "ide," right? But it doesn't say dihydrogen sulfide. You didn't use the Greek prefixes here. Okay, note that even the order of writing the elements in the formulas for hydrogen compounds is irregular. In water and hydrogen sulfide, hydrogen is written first, whereas it appears last in the other compounds, right? So with ionic compounds, it was always cation first and anion second. And what you can think about is when it comes to molecular compounds, it's the typical convention is going to be the more electropositive element or elements first, and then the more electronegative elements second. But what they're indicating to us here is that when it comes to hydrogen in molecular compounds, the naming conventions and the way you write the chemical formulas, the ordering, is going to seem pretty random, right? You're going to have these non-systematic names. You're not going to be using the Greek prefixes. The order is going to be different depending on the circumstance, etc. Okay, writing formulas for molecular compounds is usually straightforward. Thus, the name arsenic trifluoride means that there are 3 fluorine atoms and 1 arsenic atom in each molecule, and the molecular formula is ASF3. Note that the order of the elements in the formula is the same as in its name. And yeah, the general rule is going to be that the more electronegative element is going to go second in the chemical formula. Now, you might be wondering, well, what about ternary molecular compounds, even more than that, right? Molecular compounds with 5 different elements. Well, we're not going to be getting that deep. The end of this chapter is more of an introduction to nomenclature of compounds. Okay, so this chart is just a review of everything we've talked about thus far. We've been talking about the naming of inorganic compounds, and specifically we've talked about ionic and molecular. So now the next compound that we're going to talk about is acids and bases, the naming of acids and bases. Okay, acids. An acid can be described as a substance that yields hydrogen ions when dissolved in water. H+, the hydrogen ion, is equivalent to 1 proton and is often referred to that way. Formulas for acids contain 1 or more hydrogen atoms as well as an anionic group. Anions whose names end in "ide" form acids with a hydro prefix and an "ic" ending, as shown in table 2.5. Okay, so what they're saying is with an acid is going to have 1 or more hydrogen atoms attached, with the hydrogens in more of that metallic type state. They're pushing electrons away, and these hydrogens are going to be attached to an anionic group. So it's not an anion, but it's more, we're talking about molecular compounds here, just more of a negative charge skewed towards everything that's not the hydrogens. We just call it the anionic group. And if the anionic group is an "ide" name, which isn't always going to be the case, but for a lot of cases it is, then the acid name is given by, so you start with hydro, then you put you start to state the "ide" name, but instead of saying "ide," you replace the "ide" with "ic," and then say acid. So you have hydrogens attached to fluoride, that's going to be hydrofluoric acid. You have hydrogens attached to chloride, that's going to be hydrochloric acid. So again, if you've got hydrogens attached to an anionic group, that's an acid. 1 or more hydrogens, right? Here we've got 2 hydrogens. That's an acid. And then if that anionic group is an "ide," right? Because we didn't just use the name "ide" for pure anions, that were actually a pure negative charged anion, right? We used "ide" even with, we've been using "ide" even with molecular compounds as well. And so if for an acid, if the anionic group is an "ide," then you do hydro, do the "ide" name, replace the "ide" with an "ic," acid. That's the name of the acid. Okay. Now it says, in some cases, 2 different names seem to be assigned to the same chemical formula. So hydrogen chloride and then hydrochloric acid. So what's going on here? Well, the name assigned to the compound depends on its physical state. In the gaseous or pure liquid state, HCl is a molecular compound called hydrogen chloride. When it is dissolved in water, the molecules break up into H plus and Cl minus ions. In this state, the substance is called hydrochloric acid. Yeah, so I mean, it really depends on the context. So like if you're in a lab and you're planning on working with acids, you're going to be dissolving these substances in water that are going to yield H plus ions. But just because you have some liquid hydrogen chloride sitting on the table, oh, well, you can't call it hydrochloric acid. Well, no, in that context, it's going to be used as an acid, right? That's one way you could look at it. I mean, or you could be strict about it and say, look, if it's not dissolved in water, it's not an acid. And I'm not going to refer to it that way no matter what. Oxoacids are acids that contain hydrogen, oxygen, and another element called the central element. The formulas of oxoacids are usually written with the H first, followed by the central element, and then the oxygen. So oxoacids, these are acids, so they've got hydrogens attached to an anionic group. But in this case, with oxoacids, the anionic group is going to contain one or more oxygens and some other element called the central element. Okay, so we use the following 5 common acids as our references in naming oxoacids. So carbonic acid, chloric acid, nitric acid, phosphoric acid, sulfuric acid. And this is a little bit different than these anionic groups. You know, CO3 2- aren't ides. It's not carbonate, it's carbonate, chlorate, nitrate. So that's why the naming convention isn't hydrocarbonic acid, in the case that these were ides. But okay, we're going to use these as reference oxoacids. And so it says often 2 or more oxoacids have the same central atom but a different number of oxygen atoms. Starting with our reference oxoacids, whose names all end with -ic, we use the following rules to name these compounds. So with these as reference, if you add 1 oxygen to the acid, then the name is going to be, you just add a per to the front of the name of the acid. So with chloric acid, if you add an oxygen, HClO4, that's going to be perchloric acid. If you have H2SO5, that would be persulfuric acid. Removal of 1 oxygen atom from the acid, then you don't add anything out front, you just change the -ic to an -us. So nitric acid, if you remove a single oxygen, that's going to be nitrous acid, HNO2. H2CO2 would be carbonous acid. Removal of 2 oxygen atoms from the acid, then you leave the -us and you add a hypo out front. Thus, HBRO3 if you remove 2 oxygens, HBRO, that's going to be called hypobromous acid. Okay, the rules for naming anions of oxoacids, are as follows. So, yeah, if you remove 1 or more hydrogens from an acid, you're going to be left with an anion. So what are the names of the corresponding anions of oxoacids? We're still talking about oxoacids. When all the hydrogen ions are removed from an -ic acid, the anion's name ends with 8. For example, the anion CO3 2- derived from H2CO3, which is carbonic acid, is called carbonate. So yeah, we've got, if we come here, we're referring to -ic acids here. So there's 2 -ic acids. You have here's our reference acids, but if you add a oxygen, then you get a per-ic acid. And so if you removed all the hydrogens from any of these -ic acids, then what you do is there's no more hydrogen, so it's no longer an acid anymore. You remove the acid and you replace the -ic with an -us. So like even if you add perchloric acid. Well, okay, if you just remove the hydrogen here, then you're left with chlorate. It's not an acid anymore, you have chlorate. If you had HClO4, that's perchloric acid, and you remove the hydrogen, then that's going to be perchlorate. It's going to be the ion. You replace the -ic with an 8. Okay, when all the hydrogen ions are removed from an -us acid, the anion's name ends with, instead of 8, you do ite. Thus, the anion ClO2 minus derived from, so chlorous acid is called chlorite. Yeah, because we had, here's chloric acid, but you removed a single oxygen, so now it's chlorous acid. But now if you remove the hydrogen from that, since it's an us acid, there's no more acid, and you replace the ic with an ite. But it would be also us acids are the hypoacids. So if you're dealing with a hypoous acid and all the hydrogens are removed, then it's going to be a hypoite acid. Okay, the names of anions in which one or more but not all the hydrogen ions have been removed must indicate the number of hydrogen ions present. For example, consider the anions derived from phosphoric acid. So yeah, in this case, if you have an ion of one of these oxo acids with not all the hydrogens but just some have been removed, you're still going to use the name that corresponds to with all of the hydrogens being removed. Except when there's some hydrogens left, you're going to put, it's going to be a two-part name. With the first part's going to have hydrogen, and then you'll use the necessary Greek prefix. So here we've got phosphoric acid. If you remove all the hydrogens, you've got phosphate, right? So now, we're, for H2PO4 minus, instead of just putting phosphate, we're going to do dihydrogen phosphate. Here we'll do just hydrogen phosphate. We don't need to put a mono. And then here we'll just have phosphate. That's the idea. So yeah, we didn't need to put the mono. And then let's see. Here they give examples with, so perchloric acid. Yeah, here's a peric acid, perchloric acid. What's the corresponding, if you remove the hydrogen, what do you get? Perchlorate. Now here we've got chloric acid. We've added an oxygen, so now that's going to be chlorate. Yeah, they're going through the different the ics and the us's here. And in this case, you just remove one hydrogen and you're left with the full ion with no hydrogens. But then if you had another case where you had to remove, it was H3 something and then H2 and then H1, you would just put the dihydrogen, then put the ion name, the full ion name, or trihydrogen, whatever. Okay, now naming bases. A base can be described as a substance that yields hydroxide ions when dissolved in water. Some examples are sodium hydroxide, potassium hydroxide, barium hydroxide. Ammonia, NH3, a molecular compound in the gaseous or pure liquid state, is also classified as a common base. At first glance, this may seem to be an exception to the definition of a base, but note that as long as a substance yields hydroxide ions when dissolved in water, it need not contain hydroxide ions in its structure to be considered a base. In fact, when ammonia dissolves in water, NH3 reacts partially with water to yield NH4 plus and OH minus ions. Yeah, because it takes a hydrogen from the H2O molecules to make NH4 plus, which results in OH minus ions. Thus, it is properly classified as a base. So yeah, as far as naming bases, a lot of bases are going to have these hydroxide groups, OH minus groups, OH minus anions, right? We talked about hydroxide earlier because the NaOH is an ionic compound, right? The OH minus anion is a common anion in ionic compounds. So you have ionic compounds with a OH anion are going to be bases, because we're going to learn in a couple of chapters that ionic compounds are all strong electrolytes. So an ionic compound is going to dissolve in water. And so what they're showing here is that if you have an ionic compound with an OH group, and so that means it's going to be a base. Well, unlike acids, we're not going to use with an acid, you had its name was like hydrogen chloride. If it was just existing, not in the context of being dissolved in water, but if it was in the context of being dissolved in water, it had a name, its own acid name. But here, they're indicating that when it comes to bases, It doesn't have its own special base name. You just use its regular chemical compound name. So sodium hydroxide is just sodium hydroxide no matter what the context is. Okay, hydrates. Hydrates are compounds that have a specific number of water molecules attached to them. For example, in its normal state, each unit of copper 2 nitrate has 5 water molecules associated with it. The systematic name for this compound is copper 2 sulfate pentahydrate, and its formula is written as, so the copper sulfate chemical formula, then with 5 H2O molecules. So yeah, you can think about this idea of a chemical compound being hydrated, like if you dissolve sugar in water, then anything dissolved in water, whether it be ions dissolved in water or neutral molecules, are hydrated. They're surrounded by, they're fully attached to water molecules, but you can still be hydrated and not be dissolved in water, right? So what they're saying here is that hydrates, it doesn't mean that you have to have as many water molecules as possible attached, which would be the case if you're dissolved in water. As long as you've got some number of water molecules attached to you as a chemical compound, then you're considered a hydrate. So a hydrate is just going to have, you're going to state the name of the compound. So here, copper 2 sulfate, and then next you're going to say hydrate with the proper prefix out front to indicate the number of water molecules. That's it. You're a hydrate if you have any water molecules attached to you in any context, dissolved in water, whatever, then you just state the name of the compound. You're going to be a hydrate, and you just put the Greek prefix in front of the hydrate to indicate how many water molecules are attached. In this case, there's 5 water molecules attached, so you have copper 2 sulfate pentahydrate. The water molecules can be driven off by heating. When this occurs, the resulting compound is just copper 2 sulfate, which is sometimes called anhydrous copper 2 sulfate. Anhydrous means that the compound no longer has water molecules associated with it. So, yeah, this is all about context. This is similar to when you refer to a compound as an acid or just as use its regular compound name. In general, when you see CuSO4, that's copper 2 sulfate. In general, but if it's within the context of it's a copper 2 sulfate that's just been dehydrated, had all the water molecules removed, then you might want to refer to it as anhydrous copper 2 sulfate. Okay, here's some other examples: barium chloride dihydrate, lithium chloride monohydrate, magnesium sulfate heptahydrate. Okay, familiar inorganic compounds. Some compounds are better known by their common names than by their systematic chemical names. Yeah. So water. And here's its systematic name, right? Dihydrogen monoxide. Ammonia, dry ice, table salt, laughing gas, marble, chalk, limestone, Epsom salt, washing soda, baking soda, gypsum, calcium sulfate dihydrate. Again, I want to stress there's a lot of circumstances where you have hydrates that it's not like they're dissolved in water. They're just, a lot of these ores of metals, metal ores, when they mine the metals, they come out as hydrates. They're not fully hydrated like they're dissolved in water, but they still have water molecules attached. Okay, now, organic compounds. Everything we just went through was nomenclature for inorganic compounds. So now here's an introduction to organic compounds. The simplest type of organic compounds is the hydrocarbons, which contain only carbon and hydrogen atoms. So yeah, with organic compounds, they'll contain nitrogen, sulfur. There's all kinds of organic compounds associated with biological systems. But the simplest type they're saying here are hydrocarbons. The hydrocarbons are used as fuels for domestic and industrial heating, for generating electricity and powering internal combustion engines, and as starting materials for the chemical industry. One class of hydrocarbons is called the alkanes. Table 2.8 shows the names, formulas, and molecular models of the first 10 straight chain alkanes. in which the carbon chains have no branches. Note that all the names end with "-ane". Starting with C5H12, we use the Greek prefixes from the earlier table to indicate the number of carbon atoms present. So, okay, if we come to this table, this is one class of hydrocarbons called the alkanes. And here's the first 10 straight chain alkanes. And these are just hydrocarbons with no branches. So you'll have you start with CH4, then C2H6, then C3H8, then C4H10. So if you have a carbon in between the ends, it's going to have 2 hydrogens attached. At the ends, you'll have 3 hydrogens attached. And then for the case of just one carbon, you have 4 hydrogens. That's a special case where you have 4 hydrogens attached to the carbon. But once you have more than 2 carbons, if you're an end carbon, you'll have 3 hydrogens attached. If you're in between the ends, you'll have 2 attached. And the names are of these hydrocarbons. They're part of the alkane group, so they're going to end with "-ane." And then the name starts with the Greek prefix for the number of carbons in the chain. And then starting with the 5-carbon chain, the beginning of the name is going to be based on the Greek prefix corresponding to the number of carbons. So pentane, hexane, heptane. And then C4, C3, C2, C1 still end in "-ane, but the start of the name is just more of like a systematic name, just assigned to that type of chain. The chemistry of organic compounds is largely determined by the functional groups, which consist of one or a few atoms bonded in a specific way. For example, when a hydrogen atom in methane is replaced by a hydroxyl group, an amino group, and a carboxyl group, the following molecules are generated. So you take methane and replace one of the hydrogens with a functional group, a hydroxyl, an amino, or a carboxyl. These functional groups are going to change the chemistry of these molecules. The chemical properties of these molecules can be predicted based on the reactivity of the functional groups. Although the nomenclature of the major classes of organic compounds and their properties in terms of the functional group will not be discussed until chapter 24, we will frequently use organic compounds as examples to illustrate chemical bonding, acid-base reactions, and other properties throughout the book.